Okay, go.
Okay, so you all have a letter that needs to go home, and when I find out more about what the assessment will be for your exam grade, I will let you know once I get clarification on that. One of the things I want to make sure we do is the exam review that you got from Mr. Daughtry. I want to go over the correct answers that you've been working on and also how you would get those correct answers so that you understand the concepts you've gone over so far. Starts off with kinematics, which is like those linear equations that we previously went over. Dynamics, that's like F equals ma, things accelerating. Something that's dynamic just means it's changing. That's all it really means. Then we'll talk about energy, momentum, and we'll see how far we get, whether or not we get to this or not. Okay, so want to go to the correct answers? Please ask questions as you have them. So if you have this, that would be a great time to get that out. We're going to go through it and go over some of the correct answers. See a little better?
Much better.
All right, topics covered. You have an online resource and also units, SI units. So those units you want to make sure you're working in so that your answers are correct. These are the same three equations that we talked about last time. Acceleration is a change of velocity over a change of time. So from that, you can get this first equation. It's hard to read here. I'm just going to rewrite them over here, but they're the same as yesterday. V equals VO plus AT. What does the T stand for?
Time.
Time measured in seconds. A is acceleration, which is measured meters per second squared. How is V and VO different? What is VO? It's the initial velocity or original velocity. V is the final velocity. Velocity's units are meters per second. The next equation we have V squared equals VO squared plus 2A delta x. X just means the distance or displacement. Okay? For linear acceleration, that distance or displacement could be horizontal, could be vertical. Anytime you have uniform acceleration, that means constant acceleration, you can apply these equations. Finally, you have an equation that is the x equals xo plus equals VOT 1/2 AT squared. Oftentimes, that xo is left out because that just means if you start from a place that's not at the origin, you could just add that distance to whatever your answer is. It's kind of not really necessary to put in the equation. Okay? All right, let's keep going here. So, previous quiz questions. I want to go over how you would know that those are the answers and what you did to solve them. A toy car goes 3 meters due south, then 6 meters per second due west. If this were a vector problem, you could simply draw your vector south and your vector west and find the hypotenuse. But since this is just asking for the average speed, speed is a scalar, not a vector. You don't have to worry about the direction. Speed is when you take the total distance divided by the total time. The total distance traveled is first the 3 meters south that you went, so there's 3 meters, plus what's the distance you traveled west? If you went 6 meters per second for 2 seconds, you've gone a total of 12 meters west. So you went 3 meters south, 12 meters west. Divided by the total time. How many seconds did it take you to do this whole thing? 3 seconds. You did this for 1 second, that for 2 seconds. Divided by 3 seconds. So your speed, you have 15 divided by 3, or 5 meters per second. That's why your answer is 5. Car approaching an intersection on wet pavement. If you want to decrease the distance that it takes for you to stop, you want to find out, well, how much slower do you need to go? One way to illustrate that is you could use an example. For instance, looking at the equation v squared VO squared plus 2AX, I'm going to turn on this front light just so you can see what I'm doing. If you're coming to a stop, what's your final velocity going to be? 0. The beginning velocity, I'm going to make up some numbers first. For instance, let's say you're going 10 meters per second, and you can find your acceleration if you want to stop in, let's say, 50 meters. Yeah, I'm just going to do an example. Going 10 meters per second, you stop in 50 meters. What's your acceleration going to be? What's 10 squared? 100. And then if you divide 100 by 2 times 50, 100 divided by 100 makes it easy. And why is my acceleration negative? What does that mean? Because you're slowing down or stopping, the acceleration is negative. Let's use the same numbers, but now I want to find the velocity. If I want to stop in half of the distance, I'm not going to use 50 meters, I'm going to use what? 25 meters. We're going to assume the same acceleration, -1. I plugged everything back in that I did up here, and now I'm going to look for the new velocity if I have half the distance. If you do that, you solve, you have 2 times 25, that's 50. Square root of 50, it's a little bit more than 7. It's actually 7.07 meters per second. 7.07 meters per second versus 10 meters per second. .7% of your original velocity, which is about 71%. So that one is a little bit more involved. But let me ask you another question related to that. Let's say if you're traveling twice the speed, how much more distance would you need to stop? If you travel twice as fast and it's squared, then how much more distance do you need to stop? 4 times. So because it's squared, like if you're going 10 meters per second and you square it, versus 20 meters per second and square it, went from 100 to 400, that's 4 times the distance. Does that make sense? You can either put in coefficients, or you can solve it with an example and you get the same answer. Also, it's 0.707 because it's the square root of half. If you're putting in coefficients and you want to say half the velocity, or half the distance, and you put in half, and it's squared, well, the square root of 1/2, it's 0.707. There's a lot of different ways you can think about this to get to the same answer. Wile E. Coyote runs off a cliff chasing Roadrunner at 10 meters per second. When you see meters and then seconds to the -1, that's the same thing as saying 10 meters per second. It's just on the bottom. That's a velocity. Lands on the ground below, 20 meters from, it just went dark. That's how bad it went. So have you all done horizontal launch problems before, horizontal velocity?
Yeah.
Okay. Yeah, last class had some difficulty remembering exactly how to approach these, so I just want to go over some ideas. If you have something, these are called horizontal launch because something has an initial horizontal velocity and falls off the edge. It could be Wile E. Coyote, it could be a ball rolling off a table, it could be someone hitting a tennis ball horizontally. Any of those count. You really only need to know 2 things, 2 equations. X equals the velocity times time. This just comes from distance is velocity times time. X is the horizontal distance. Y is the vertical distance. Y equals 1/2 gt squared. Y equals 1/2 gt squared actually comes from this equation because the beginning velocity in the y direction is 0, so that term goes away. The distance is down in the y direction. The acceleration is due to gravity. All right, so if you are 20 meters, lands 20 meters from the paint, let's see. All right, so you land 20 meters out. If you're traveling at 10 meters per second and you land that distance out, he lands 20 meters from the base of the cliff while traveling 10 meters per second, and you want to find the time. So what's the time going to be for Wile E. Coyote? How long is he in the air for? He's in the air for 2 seconds. And if you were asked about time, you'd be done. However, you want to know, well, how high is the cliff? If he's in the air for 2 seconds, how high was the cliff? Well, you can use that other equation, y equals 1/2 gt squared. Y is the distance, the vertical distance you're looking for, equals 1/2. Gravity is 9.8 or negative 9.8 to indicate the direction times the time of 2 seconds, which is squared. So now we have half times 9.8 times 4, which looks like 19.6. So 19.6 or negative 19.6 meters is your answer. And the reason it comes out negative is because Wile E. Coyote is falling down. If gravity is negative 9.8 down, then that makes the distance down negative. That's all it means, it's a direction. And so if your answer is 19.6, that's very close to this answer of 20 meters. All right. Is this making sense so far? Because you would stop me and ask me if you have questions. Turn the light back down so you can try to see this graph, but also if you have your handout, it's probably easier to see than what's up here. But on your handout, you have an example of a velocity versus time graph here. You remember seeing velocity versus time? A little bit, position versus time and velocity versus time graphs. All right, it's another way of getting information. Let's do this. It's another way of getting information related to acceleration, but instead of paragraph form, it's just illustrated here. For instance, this object, person, thing, whatever it happens to be, starts at 0. In other words, they're not moving. Then when time starts, they speed up to 10 meters per second. What's the acceleration during this time from 4 to 10 seconds? The acceleration is 0. Does that mean the person has stopped? No, it just means that they're maintaining a constant velocity of 10 meters per second. From 10 seconds to 14 seconds, what's this person or object or thing doing? Decelerate. They're slowing down in the positive direction. This looks like one continuous line. That doesn't mean they're maintaining the same direction and speed, however. If I were to try to walk this, like let's call that the positive direction, which is to your right, I would start from rest, and then I would start to speed up, and then I'm going 10 meters per second, I maintain that, and then as you slow down, you're still going in the positive direction, but where you reach that axis, you actually turn around and you start coming back the other way. That's why it goes negative. When the velocity goes negative, you're actually returning back to where you started. And then you're coming back at a negative 5 meters per second, and then you slow down and you stop again until your velocity is 0. What do you get when you find the slope? The acceleration. This is the change of velocity over the change of time. The rise over run. Acceleration is change of velocity over change of time. That's the rise over run. If you go from 0 to 10 meters per second in 4 seconds, what's your acceleration if you change 10 meters per second over 4 seconds? 2.5 meters per second squared, right? So that's your acceleration. You already said your acceleration is 0 here. So here, your acceleration is negative. You take that change of velocity over time. Here, the acceleration is 0 again, and then you return. So looking at these, I kind of went into way more detail than I probably needed to, but looking at this graph, which of these is true? Object is not moving from 4 to 10 seconds. Well, as you already mentioned, you are moving. You're maintaining constant velocity. There's just no acceleration. So that's not correct. B, the average acceleration of the object during the first 2 seconds and the last 2 seconds are different. That's actually not true because even though they're in different places, the acceleration is the slope. It's the rise over run. If you find the rise over run here and the rise over run here in the last 2 seconds, the slopes are exactly the same. The acceleration in the first 2 and last 2 seconds are the same. C, 4 and 10 seconds, that has twice the speed as 16 to 34. Speed is a scalar, so you're just looking at the overall velocity without regard for direction. Here, what was your speed? 10 meters per second. What's your speed down here? Negative 5 meters. It's 5 meters per second. Negative just indicates direction, which we're not worried about when it's talking about speed. So your answer is actually letter C. The last one, D, the object is moving backwards between 10 and 14 seconds. Not entirely true because from 10 to 14 seconds, you're traveling forward, you're just slowing down, and then once you actually stop, you start speeding up in the negative direction. So that's why C is your best answer. How far did the object travel from 20 to 30 seconds? Here's 20 to 30 seconds. To find the distance traveled, your distance is velocity times time. What was your velocity from 20 to 30 seconds? 5 meters per second for 10 seconds. So if you go 5 meters per second times 10 seconds, how far do you go? 50 meters. It's 50 meters in the negative direction, but it just asked how far did you go. It didn't say what's the displacement. All right? Abigail's reaction time is twice that of Zoe's reaction time. Let me turn on this front light again. Using the equation for x VOT 1/2 AT squared, beginning velocity when you drop something is 0. So if you have twice the time, how much farther will the distance be? 4 times. It's the same thing as if you use y equals 1/2 GT squared. Either way works. If you say y equals 1/2 GT squared, let's say the reaction time, let's make up reaction time. 1 is 1 second. If you use 1 second, you have 1/2, 9.8, you can find out how far the object would go in 1 second. If you drop something, how far does it go in 1 second? Turns out it's about 4.9. And the negative again just is because it falls down. It's a direction. Versus if you drop something, how far does it go in twice the time? Well, that's 2 seconds. Well, 2 squared is 4. That's 4 times as far as it was here. 4 times 4.9, 19.6. So doubling the time gives you 4 times the distance. What do you think would happen if we tripled the time and time is squared? What would the distance be? 9 times, because if you put in a 3 here, 3 squared is 9. So when you triple the time, you will get 9 times the distance. All right, but to answer the question, 4 times as far because we doubled the time. Which two graphs correctly represent the motion of an object moving with a constant speed in a straight line? So something traveling at a constant speed at a straight line. When you're traveling at a constant speed, you're covering the same amount of distance per unit time, because speed is distance over time. So this first one is true because your distance is 0, but you're constantly maintaining more and more distance per unit time. The slope is constant. It's a straight line, distance versus time. This is a constant velocity. This is not constant because your speed starts at 0 and you're continuously speeding up. This would be a constant acceleration if you're going in a straight line, but it's not a constant speed. This one, acceleration versus time, this is showing you that the acceleration is constantly picking up. You're traveling faster and faster each second that goes by, and your acceleration is increasing, which is a completely different variable that we're not even worried about. That's definitely not true. And then this last one, if you were to graph your speed versus time, well, if your speed is constant, this is a straight line. So a straight line going up, distance versus time, that's a constant speed. Or if you have speed on the axes, that's a constant speed. So A and D both indicate a constant speed, the other two do not. A ball is kicked with initial velocity 12 meters per second in the vertical direction, 16 in the horizontal direction. Well, when dealing with projectiles, however fast the object goes up, the object will return and go the same speed when it comes back down to the same height. So, so if something is going up at 12 meters per second, and at the same time horizontally 16 meters per second, that's your overall velocity. When it goes up, it's going to come down and be doing the same thing. So it's still going to be going 16 meters per second horizontally, because when something is launched, the velocity in the x direction stays constant. In the vertical direction, you have constant acceleration, and the object's going to be coming back down at 12 meters per second. So the way you find the overall speed is if it's going horizontally 16 meters per second and down vertically 12 meters per second, Your overall speed is that hypotenuse. And do you recall how to find that hypotenuse? What would you use? The Pythagorean theorem. That a squared plus b squared equals c squared. And so this missing side, that hypotenuse, in this case it's actually like a 3, 4, 5 triangle, must be about 20 meters per second. Maximum height of a projectile launched with an initial vertical component. So the vertical component is 10 meters per second. The maximum height. If you're just looking at the path up, a couple ways you can do this. You can look at the linear acceleration equations and say, well, if I just look at the path going up, for instance. To use linear acceleration, remember, you should be able to identify 3 givens. It doesn't look like you have 3 givens, but you really do. The 10 meters per second, what is that? It's our initial velocity, right? It's initially going up 10 meters per second. If we're just looking at the path up, because we're trying to find that distance up, what's the velocity at the highest point going to be? It's momentarily going to go to 0. So the final velocity is 0, because looking at the path up, if you throw it 10 meters per second, when it reaches the highest point, it's going to go to 0 momentarily. And finally, anything that's in the air, whether you throw it down, throw it up, throw it across, doesn't matter. What do we always know? That's right, the acceleration due to gravity, negative 9.8 meters per second squared. And what we're looking for is the displacement. So then you look at which equation has your givens and your unknown so that you can solve it in one step. Would you want to use equation 1, 2, or 3? 2 looks like it has everything we need in it there. The final velocity is 0. Beginning velocity is 10. Times negative 9.8 for your acceleration, find your distance. So we've got 100 divided by 19.6, looks like about 5.1 meters. Maybe that was one of your choices. I think so. Hope so. Yeah, it sure is. So that's why that was 5.1 meters. All right. Projectile launched at 37 degrees. So now we have an angle launch problem. This is good for a horizontal launch. That's all you need. That means something that's just going horizontally. And you know it's horizontal because no angle is given. Here we have one where there is an angle given. You recall we're doing projectiles with angles? A little bit? Maybe? Might have done it, might not remember how to do it. Let's do that one. All right, projectile launch, 50 meters per second. (37 degrees). First thing you'd want to do, like any vector, is find the components. Components are the velocities in the x and y direction. So for instance, I don't know if you have a list of equations to do this or not, but for angle launch, in case you don't remember, first thing you want to do is find the components. When your angle is measured from the horizontal, which typically it is, you can find the velocity in the x direction by taking the velocity. This is the adjacent side. So we can do v cosine theta. And what do you think you would do to find the opposite side, the velocity in the y direction? The opposite, so v sine. That'll give you your two components, the velocity in the x and y direction. It just makes a triangle. So 50 degrees at 37, or 50 meters per second at 37 degrees, that gives you velocity in the x direction, which stays constant the whole time it's in the air. Your initial velocity in the y direction using sine. When you do that here, you get 50 cosine of 37 degrees and 50 sine of 37 degrees. Your calculator needs to be in degrees, otherwise you're going to get some odd answers if you're in radians, by the way. But you get about 40 meters per second and 30 meters per second. Really, that's all we need to do to answer this question, but we could keep going and solve for it if we wanted to. It'd be a lot of fun. It's not going to have a greater range than 45 degrees. 45 degrees is the angle at which objects achieve the maximum range. If you want to launch something as far as you possibly can, 45 degrees is your magic number. Let's say you launch something at 30 degrees. What other angle do you think will achieve the same range as something launched at 30 degrees? 60. 30 degrees and 60 degrees will actually achieve the same range. Now, they won't be in the air at the same length of time, but they'll go the same distance. They are complementary. It works out that way. It's nice. What about if you launch something at 20 degrees? What other angle should give you the same range? 70. Complementary, meaning that they add up to 90 degrees. So when you have complementary angles, things launch with the same speed, they'll achieve the same distance. In this case, let's say you want to find out how long the object is in the air. You can use this equation to find the time up and double it. And what you're really doing is taking 2 times that initial velocity in the y direction, divided by gravity. The velocity in the y direction was 30, divided by 9.8. And you can see that the object will stay in the air a little bit more than 6 seconds. 6.14. Let's say you want to find out how far it goes. Remember this equation going in the x direction? The velocity in the x direction stays the same the whole time. So you can take that velocity in the x direction of 40 meters per second. And if it goes 40 meters per second for every second it's in the air, and it's in the air for 6.14 seconds, you can figure out how far down the field it would go. About 246 meters. So this is an angle launch problem where your first step is to find that velocity in the x and y directions. Like any vector, you find its components. If you want to find the total time in the air, if it goes up and comes down at the same height, do 2 times the velocity going up divided by gravity. And this will give you the maximum range. You could use this to find the maximum height. But you want to be careful because you use half of this time, because remember it goes up half the time and down half the time. So there's a lot of stuff you can do just with linear equations and projectiles. All right. All right, so next section here is all about the mechanics, the dynamics. Dynamic, if something's dynamic, it means it's changing. So acceleration, this is the chapter where you dealt with forces, F equals ma, Newton's laws, things like that. Okay. I'm going to erase the board while you get that down there. The most commonly used equation in physics is F equals ma. F equals ma means the net force on a mass causes an acceleration. You will oftentimes find a line or arrow over the force and the acceleration because what does that mean? They're vectors, they have a direction, they can be negative. You can have a force to the right or to the left. Mass is a scalar. It doesn't make sense to have something 12 kilograms west. It's not really a mass. Oftentimes you'll also see the sigma in front of the force. That just means the sum of all forces. That's a sum of sign, sigma. But that's really F equals ma. Did you talk about an equation known as friction? Force of friction? Pretty much? Sure. Coefficient of friction times normal force. The force of friction is oftentimes referred to as the fun equation. Okay, bad joke. Too early? Okay. It's not that bad. All Alright, so force of friction, another popular equation in this section. So let's look down at the, see how far we get. So I have an example of a block that's on a table connected to a pole with another block. Very common type of problem in physics. Do you recall something, drawing forces called the free body diagram? A little bit? That's where you illustrate the forces on. Like for instance, this object on the table has a force of weight. That's creepy. It's a little weird. I'll use that one. The force that's acting down, the mass times gravity, that's the object's weight. Do you know what you call the force that acts perpendicular from a surface that comes from the surface back on the object? It is the exact same force, referred to as the normal force. A normal force is exerted by a surface on an object. In this case, they are the same. When would they not be the same? If you're pushing down on the object, pulling up on the object's on an inclined plane. Those are examples where the normal force and weight are not going to be the same. If something's pulled by a string, rope, chain, whatever, what do you call that kind of force? There you go, tension. If there's friction between the block and the surface, if the block's being pulled to the right, what direction do you think friction would go? To the left. Friction always opposes motion. It makes things difficult. That would be the direction of friction. So drawing a free body diagram means illustrating the forces on an object. This object also has a weight straight down and a tension going up. These tensions are the same because that's the same string. So if you had to draw a free body diagram, that just means you're illustrating the forces on the object. Now, let's say you want to find the acceleration, because that is the point of this question. Because F equals ma, we can solve this for A, for acceleration, and have the net force divided by the mass. What force, which weight, causes the two objects to accelerate? 3m or m? M. It's because the one's hanging off the side here that there's any acceleration. Without this block, you just got a block sitting there. So the net force is because of the motion, this mass times gravity of this block. And if we had friction, we would subtract friction because that would take away from the net force, but it's frictionless, so we don't worry about it. And we divide by the mass that accelerates. Which mass accelerates? Does m accelerate, does 3m accelerate, or do they both accelerate? They both do. They're connected by a string. This mass cannot fall down any faster than this one gets pulled to the right. The total mass of m plus 3m is 4m. M is on the top and bottom. This leaves you with gravity divided by 4. That's your acceleration, g divided by 4.
Question.
I think we have time to do another one of those, maybe with real numbers. I have a 4 kilogram mass on the table, 1.2 kilograms hanging off the edge. One common mistake is people will think that unless this mass hanging off is larger than this one, then nothing's going to move. But that's not actually true. It doesn't take much mass to move this as long as the friction is low. The weight, the normal force, the tension, the friction. The weight, the tension. When you see problems like this on an AP exam, they always ask you to draw or label the free body diagram. That's what they mean. You just label the forces. But anyway, acceleration, net force over the mass What are we gonna do to find the net force? Do you think? Which block causes them both to accelerate? The 1.2 hanging off, right? So the 1.2 kilograms is exerting a force down because of its weight, 9.8 meters per second squared, divided by the mass that accelerates. Which mass accelerates, the 4, the 1.2, or both? Both. So you get about 2.26 meters per second squared, or if you want it in significant digits, it might be 2.3. Means the same thing. Now, if you had 9.8 as a negative 9.8, that just indicates direction. So even if you had an acceleration of negative 2.26, all that means is you're counting this as the negative direction because you're getting pulled down. So if you count gravity as negative because it's down, that's fine. It doesn't change this number. Your picture illustrates the direction. All right. So that's the last one that I wanted to get through today. Keep the packet that you have now. We're going to do some more tomorrow and try to further explain all of these things, and I'll find out more about that alternate assessment exam, what that means for you all. Try to find that out for tomorrow. Okay. All right.